Hello everyone. Let us today discuss about the decision regions and probability of error calculations for different modulation techniques. Now, let us start with a very basic modulation scheme, which is binary pulse amplitude modulation. This is the most basic modulation scheme, and let us try to understand what is the meaning of calculating the probability of error and how to proceed for this particular modulation scheme, and then how to go for some complex modulation schemes. Now let us try to understand this constellation diagram in which 2 points, these are the two crosses and these are the 2 points for binary pulse amplitude modulation. Now the distance between the 2 points is d, and from the origin the distance of each point is d by 2. So that means this point will be plus d by 2, and which is x naught, and x1 will be minus d by 2. Now we will calculate the average probability of error, and which is usually denoted by PE very commonly. Now, what is probability of error? Probability of error, how when we will make the error, right? Now, this if this uh, one of the points will be transmitted from the transmitter side, and we will receive a signal at the receiver end. Now, let us say that received signal is y. Now, let us suppose that if this point x naught was transmitted, but what we received, the amplitude that we received is less than 0. Uh, we transmitted plus d by 2, but we received an amplitude which is we received a signal y which is less than 0. So that means um, in that case, now what is the decision rule? Decision rule says that when the received signal amplitude is greater than 0, we will say that x naught was transmitted. When the received signal amplitude is less than 0, we will say that x1 was transmitted. So in that case, when we will make the error, we will make the error when the received signal is less than 0, but the transmitted was x naught, which is plus d by 2. We transmitted x naught at a distance from the origin, which is d by 2, but what we received is a signal amplitude which is less than 0. So that means we are making an error. Since the 2 points are equally likely points, so the probability will be half. Probability of error associated with these 2 points will be half. So half the probability of error, probability when y is less than 0, given x naught was transmitted, which is at a distance of d by 2, right? And plus when we transmitted x1, which is at a distance of minus d by 2, but we received an amplitude which is greater than 0, so again we will make an error. So these two probabilities will add up, right? So what is y plus y is equal to x plus n, right? So this is how we define the probability of error, that half the probability when y less than 0 but transmitted was x is equal to plus d by 2, and plus half probability when y is greater than 0 given x equal to minus d by 2. Now what is y equal to? Y equal to x plus n. So we can replace this y here. Y, so this is half probability of x plus n less than 0 given x equal to d by 2, plus half x plus n greater than 0 given x equal to minus d by 2, right? So uh, so in that case, if we put the value of x equal to d by 2 here in this inequality, so what we will get is n is less than my probability, half probability n is less than minus d by 2, plus half probability n greater than d by 2. So this is when we put the values of x, particular in this case, let us put the value of x to be d by 2, and in the second term, excuse me, in the second term, let us put the value of x to be minus d by 2. In that case, this is half probability n less than minus d by 2 plus half probability n greater than d by 2. Now let us see, because we know that the noise is Gaussian, we are assuming that the noise is Gaussian. So uh, taking the Gaussian shape, this point is plus d by 2 and this point is minus d by 2. So area under the curve beyond this point will be probability of probability that n is greater than d by 2, and along this side if we take the area under the curve beyond minus d by 2, it is probability n less than minus d by 2, right? So both the areas under the curve are symmetric. In that case, since it was half plus half, half plus half, so since the two areas under the curve are symmetric to each other, so therefore we can say that it is probability of error is actually equal to probability of n greater than d by 2 or probability of n less than minus d by either one of the two, because in this case n is Gaussian distribution with zero mean. Now, if you look at this probability, this is difficult to compute in a closed form solution. So, what is this given by? This is given by integral d by 2 going from d by 2 to infinity 1 over, since this is I am using the Gaussian expression here, 1 over under root 2 pi n naught by 2, because sigma is n naught by 2 here in the case of noise. Sigma square is n naught by 2, which is variance, but I am putting here n naught by 2 under root is the standard deviation, e to the power minus x square 2 n naught by 2. So this 2 will cancel out. So what I will get is integral d by 2 to infinity 1 over under root 2 pi n naught by 2 e to the power minus x square n by n naught dx. So what is noise? Noise is with zero variance and n by 2 as the zero mean and n by 2 as the variance, right? So what I mean to say is that this is a difficult expression to compute in the closed form. So how to go about this? In MATLAB, there is a function called Q function and is available in MATLAB as subroutines, right, which can be used to solve this these types of expressions. Now let us try to understand what is Q function. Now Q function is defined as I have tried to explain below this. Suppose Z is a random variable. It is Gaussian again. We assume that it is Gaussian with mean 0 and variance 1. So we can represent the Z which is a random variable, and we can represent it to be n 0 comma 1. Then that's how the random variables are represented. Now what is Q function? Qx will be given by 1 over under root 2 pi integral x going from x to infinity e to the power minus x square by 2 dx. So this is how the Q function is defined. Now what is this Q function equal to? This is equal to the probability density function of this z variable integral going from x to infinity. That's the probability density function of this random variable z, which I represent as pz, right? So this point is x, and towards the right of this x is what we call as the Q function. This is the PDF of z, and area under the curve beyond x will be qx. So qx is actually the area under the curve. This point is along the x-axis is x. So beyond x will be your q area under the curve will be actually your q function. Q function is from x to infinity e to the power minus x square by 2 dx, right? And or we can also say that if we take the cumulative distribution function to the left of this point x, that will be f subscript zx. So what is this Q function then equal to? Qx will be equal to 1 minus the cumulative distribution function of z, and we denote it by probability of z greater than x. This is the probability of z greater than x. Okay. Now in MATLAB actually the ERFC function is available, which is related to QS, and you can compute these types of expression using MATLAB also. Now let's define another random variable. Now what is this random variable z? Z is given by this is Gaussian again, and just we are scaling this noise n by factor of n naught by 2. So that means why we are actually scaling it by under root of n naught by 2, so that the variance is 1. So this random variable will have mean 0 and variance 1. And if you remember, if you remember this formula where we calculated the probability of error in the case of binary PAM to be probability n greater than d by 2 or probability n less than minus d by 2. So we have to actually compute, we have to put this expression in terms of the Q function. So how can we do that? What we will do is that probability n greater than d by 2 will be equal to probability of z greater than d by 2. We will use this expression, so we will put the value of n to be d by 2 here. Probability of z greater than d by 2, that means in this expression we put value of n to be d by 2 in this expression for this z. So that means probability of z greater than d by 2 divided by under root of n naught by 2. So that means probability z greater than d by under root of 2 n naught, right? So what is this probability of z? As I have already explained you that what is Q function? Q function is actually probability of this random variable z greater than x, right? So I can write this probability of z greater than x as Qx. So in the same way, if the probability of z is greater than d by under root of 2 n naught, so I can write Q of d by under root 2 n naught. So I am writing it again. Q probability, this is equal to probability of error is equal to Q of d by under root 2 n naught. What is this? This is the probability of error in the case of binary pulse amplitude modulation expressed in terms of the Q function. Now we also know that we also if we want to put the probability of error in terms of the energy, how can we do that? The distance between the 2 points is d. What is the energy? Energy will be, so, and what is energy? Energy is the distance from the origin to the point, which is d by 2. So energy will be equal to d, this distance square. So that means d square by 4. So I can calculate d from here, which is 2 under root e. So I can replace this d with 2 under root e. So it will be 2 under root e, and this, now this in terms of energy, the probability of error expression becomes Q of under root of 2e by n naught, where n naught is the noise power spectral density. Sigma is equal to under root of n naught by 2, and sigma square is of course n naught by 2, right, which is the variance, and this is standard deviation. And if we know that sigma is under root n naught by 2, so I can replace this under root of n naught by 2 here in this expression, and I can put this probability of expression probability of error expression as Q of d by 2 by sigma, right? What is d by 2? D by 2 is the distance of the signal point from the origin, right? So this is probability of error is equal to Q of the distance of the signal point from the origin divided by the sigma. What is sigma? Sigma is the standard deviation, right? Now, now we have, what we have done is, just let me summarize what we have done. We started with the, we wanted to explain the probability of error calculation and what are decision regions. So I will come to the main part, decision regions once again. So what we did, we started with the case of binary PAM in which 2 signal points are there, right? So we say that the error will be made when y is less than 0, but the transmitted was x is equal to plus d by 2, or y is greater than 0 when the transmitted was x is equal to minus d by 2. So we went on with the calculations, and we found out that the probability of error is actually given by either one of the two, probability n greater than d by 2 or probability n less than minus d by 2. And this can be defined like this, integral going from d by 2 to infinity 1 over under root 2 pi n naught by 2 e to the power minus x square n naught by 2, because since n is Gaussian with zero mean, right? So this expression, we said that it is difficult to compute in closed expression. So therefore, there is a function available in MATLAB which is Q function. And how the Q function is defined? We take a random variable z with mean 0 and variance as 1, and I will explain how this variance has one variance as 1 has come, because once you scale the noise n by under root of n naught by 2, you will get the variance as 1. So q, what is q function? Q function is 1 over under root 2 pi integral x going from x to infinity to the minus x square by 2 dx. What is this? How can we explain this? This is explained using this random variable. What is the random variable? And this is also equal to integral going from x to infinity pz dz. What is pz? Pz is the probability density function of z, which is the random variable. And what is q function? Q function is the area under the curve, right, beyond this point x. So qx is equal to integral going from x to infinity pz dz. In other words, we can also express the q function in terms of the left side of this point x, which is actually the cumulative distribution function. So it will be qx will be equal to 1 minus the f subscript z x, which is the cumulative distribution function of z, and we can express it to be probability z greater than x. Probability z greater than x, that means area under this curve is actually qx. Now we try to further calculate the probability n greater than d by 2, and I put n equal to d by 2, so I calculated it to be equal to q of d by under root of 2 n naught. And if I want to express in terms of energy, the energy of a signal point is the distance from the origin. So it is d by 2. So therefore the energy is d square. Energy is distance square, which is d square by 4. So d I calculated from here to be 2 under root e. And further I made the calculations and I found out that probability of error is actually q function of d by 2 divided by sigma. What is d by 2? D by 2 is the distance of the signal point from the origin. So this is how we are able to calculate the probability of error in binary pulse amplitude modulation. But if you take any binary modulation scheme, either if you take a binary frequency shift king or any other orthogonal binary signal set, so if it is orthogonal binary signal set, that means the 2 points will be orthogonal to each other. So what is the distance between the 2 points? So distance between the 2 points will be d equal to under root of 2es, because in that case, let me, so it is this d is, we calculated this d is equal to 2 under root e. So distance from the origin will be under root e, right? So this will be under root e, this will be under root e, and you will say that this d between the signal points in an orthogonal modulation scheme will be equal to under root of 2es. And if we use the same formula, probability of error equal to q of distance between the distance of the signal point from the origin divided by sigma. So what is the distance of each point from the origin? It is under root es or e divided by n naught. So from here you can calculate the probability of error in the case of binary FSK or any, for that matter, any orthogonal binary signal set. Now let us talk about the decision regions. Actually, what is the decision region? So suppose this is the this cross here is the signal point from the constellation diagram that was transmitted, and we define a decision boundary by this vertical line. Now we say that if the received signal is on the left of this decision boundary, then we will say that this point was transmitted. But if the received signal falls on the right side of this decision boundary, then we will not say that this signal point was transmitted, and the decision will go in favor of some other signal point. So that's what I'm trying to explain. Let's say point X was transmitted from the signal set, and we will earmark an area called decision region. So this is the decision region, which is in this case on the left side of this vertical line. So that if the received signal point lies in that decision region, that means that particular signal was transmitted, else the decision will go in favor of other signal point depending on the decision region in which the signal point falls. Now, particularly to this case, what is the distance of this point from the decision boundary? This distance is, let's say, L. In that case, what is taking the same formula further, that the probability of error is actually Q of the distance of the signal point from the decision point or decision boundary. So in that case, here the distance is L, so it will be given by Q of L by E. The probability of error in this case, if this is the signal point and this type of decision region is there, we will say that the probability of error will be given by Q of L by E. Right? And if we can L by sigma, not L by sigma. So we can also replace this sigma with under root of n naught by 2. So this will be the probability of error in terms of the Q function. If this is the signal point and this type of decision boundary and decision region is there. So let's talk more about some different types of decision regions also. Let us say this is the signal point which was transmitted, and these two vertical lines are actually the decision boundaries. Now, if we express the noise vector in a two-dimensional space, we will say that n1 is the component in the x direction and n2 is the component of the noise in the y direction. So there will be two components of the noise, but let's say this signal point is L1 distance from the decision boundary and L2 distance from this decision boundary. So what is the probability of error? Probability of error will be given by when the probability that n1 is greater than L. So that means n1, because we will not consider n2, it is only in the horizontal direction. So n1 is greater than L or n1 is less than minus L by 2. Either it lies away from this boundary on this side or on this side. And this is probability of error. What is the probability of making a correct decision? The probability of making a correct decision is that we will make a correct decision if the received signal falls in this decision boundary. That means if minus L2 is less than n1 is less than L1, that the noise component is such that the received signal lies within this decision region. So this is defined by this is defined as probability minus L2 is less than n1 is less than L1. Minus L2 less than n1 less than L1. So this is probability of making a correct decision. What is the meaning of this? Let us try to because this is Gaussian, of course, so we draw the Gaussian curve. This point is L1 by sigma, this point is minus L2 by sigma. So this is the area under the curve, and this says that the probability n1 is greater than L1, and this says that the probability n1 is less than minus L by 2. Right? So these points need to be computed. So we can also say that we can express this as, we can also express this as what is the probability of making a correct decision. It is 1 minus Q of L1 by sigma this plus Q of L2 by sigma. So right, so this is corresponding to this region and corresponding to this region, the two probabilities will be added up, right, in terms of Q function. And what is the probability of making a correct decision? Because this is the probability of error for this point Q of L1 by sigma. This is the probability of error for this point Q of L2 by sigma. Both these probabilities of error are added and subtracted from 1, so that will become the probability of making a correct decision. And same is expressed here. What is the probability of error? All right, so this is the particular case when the decision region is of this form. Now let's talk more about some more decision regions. Now let us say that if this is the signal point and the distance of the signal point from this decision boundary is L1, and now the two decision boundaries we selected are perpendicular to each other. So L2 is the distance of this signal point from this boundary. Now, what is the probability of making a correct decision? Probability of making a correct decision is that probability if the noise vector makes the received signal to lie less than L1. So N1 is less than L1 and N2 is less than L2. So that means the received signal lies somewhere in between the decision region, right? And these N1 and N2 components are independent of each other. So we can say that we can write this expression like this: probability N1 less than L1 into probability N2 less than L2. And we can further use the expression, what is the probability of, this is probability of making a correct decision. So it is 1 minus q of q L1 by sigma, 1 minus q L2 by sigma. And what is probability of error? 1 minus the probability of making a correct decision. And we can solve this further and we will find out that this is the probability of error. Now let us talk about another decision region in which three decision boundaries we are selecting. This is the signal point, and we assume that all the decision boundaries are at the same distance from the signal point. We can. This is only for simplicity. I am taking this case. Otherwise, these distances can be different also. Only thing will be that the expression that we will get will be a little more complicated. So point is L distance away from all the decision regions. What is the probability of error? It is 1 minus the probability of making a correct decision. So when the correct decision will be made, when N1 is less than L and N2, this is along the horizontal direction. When this point is, when N1 is less than L, and for the vertical axis, it will be, what is N2? N2 will be between minus L to L. So N2 is between minus L to L, right? So this will be, of course, 1 minus q of L by sigma, and this term will be 1 minus twice of q. If you look at if you draw the PDF, and these two areas will be there which are corresponding to the probability of error. And what is the probability of making a correct decision? It will be 1 minus 2q L by sigma. And all this probability of making a correct decision when subtracted from 1 will give me the probability of error. And let us talk about the last decision region in which this signal point is L distance from 4 decision boundaries around it. So in that case, the probability of correct decision will be if the N1 remains between L minus L to L and N2 remains between minus L to L. And this will be squared, and this will be the probability of error calculated. So this is how we can select the decision regions and we can make the probability of error calculations, right? Thank you very much.